Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue talking about parallelism, multi-threading, and the Java util concurrent package, and we're going to look at a few of the concurrent data structures that are present in this package. So once again, you could do everything that you needed for avoiding race conditions and whatnot in just using synchronized, wait, and notify, the basic building blocks. However, some of these things you do a lot, and doing it correctly can be hard. Not just correctly, but also efficiently. And so in the Java util concurrent package, they put in a number of other classes for you that can help make things easier for you to do. So we'll go through and look at the API at some of these. The first two that I want to look at, they're right here next to each other, the countdown latch and the cyclic barrier. And the analogy that I often give to students for countdown latch or the cyclic barrier is imagine that you have agreed with a number of your friends that you're going to go out to dinner someplace. And you are all off doing your various things, but you have a car and you're going to drive to the place where you're going to dinner. When the first person reaches the car, what are they supposed to do? Well, they're supposed to sit there and wait. They don't get in the car and drive off. That would cause problems. So they're supposed to sit there and wait until the second person gets there, who also sits there and waits until the third person gets there. And then you continue this until the last person gets there, and then you can all get in the car and drive away. That's exactly the type of situation that lends itself to a countdown latch. In a program, the type of situation that might call for this would be you have a bunch of different threads working on some task, the first stage of some task, and they can't advance until they have all completed what they need to do. So when you build a countdown latch, you tell it how high the count is, so how many things need to go in there before they all continue. And then as each thread gets to this critical point, so in like the people getting to the car, they await. Now what the call to await is going to do is if you're not the last one, it basically blocks. It just sits there and you do nothing. However, if as soon as the last one calls await and you have gotten up to the count here, then all of the threads are released from the blocking and they all get to keep going. So once again, you could have written this yourself with a synchronized and await and notify, but it's all bundled here together in this nice little class called a countdown latch inside of java.util.concurrent. Now the countdown latch allows you to do this countdown once. There is also a cyclic barrier which does the same type of thing, except that and so you initialize it, tell it how many parties there are, and you call await on it. However, after everyone has gone through, you can use the cyclic barrier over and over and over again. So the work that I do is in numerical simulations, and I do these simulations of Saturn's rings, and to make them run faster, I actually need to parallelize them. And so I will create a whole bunch of different threads that are processing different parts of the ring system, but they have to kind of go in a certain lockstep. There are these time steps, and I can't have one thread going on to the next time step until all the others have finished. So that's a particular example where a cyclic barrier or a countdown latch would be useful. When I start up a time step, I send all the threads off doing whatever it is that they're doing and give them a cyclic barrier for the number of threads, and that way as each thread manages to finish its job, it will sit and wait at the barrier until they all go through, and then they can all start the next step again. Because this is an example where they would repeat, it really is a better example of the cyclic barrier. Another example of one of these concurrent data structures is the exchanger. Now the exchanger takes in Java a generic. In Scala, this would be a type parameter. Note that in Java, when you put things inside of these angle braces, in Scala they go inside of square brackets because they are type parameters you pass in. You build an exchanger, you don't pass any arguments, the way that this works is that it is intended to have two threads exchange objects and pass them to one another. So when one thread gets to a certain point, it calls exchange on the exchanger, and it passes its object of type V, whatever V might be. Who knows what it is that you're passing between the two of them. You can almost picture this as, if you go to a reference from spy movies, this is, you have two spies and they're handing off a briefcase. Well, that's what the exchanger does. Spy 1 gets to the bench and sets down the briefcase, which happens to be of type V, and then basically waits until the other party also gets to that point, and they call exchange on there, and then each one gets returned to it the value that the other one passed in. But this is completely thread safe. Now hopefully if you stop and you think about how you would write this code using synchronized wait and notify, you quickly realize that there are all types of places where this could go wrong. Okay, because of the race conditions, because of you don't know which thread is going to get there first, and if you have mutable memory, you start to worry about all types of problems. This exchanger takes all of those worries out of your hands and just makes it so that you can pass it an object and you get back an object from another thread, and you know that everything was handled properly in between. There are also blocking queues. We'll talk about the exact nature of queues in a later chapter. Actually, two types of blocking queues. There's an array blocking queue and a linked blocking queue in here. The idea of a blocking queue, picture an assembly line where you have multiple different stations and they work on building things, and the assembly happens in different steps. So maybe you have 3 people working on step A and 2 people working on step B, etc. And you need to pass objects from step A to step B to step C in a way that is safe between them. So you have, when I say people here in the program, you have multiple threads that are doing whatever the calculation A is. And they take the result of calculation A and they pass it off to some other threads that are going to do calculation B with those. Now, where things can get complex is that you can't have the threads that are doing calculation B, they can't proceed until they get something from A. So you have to be able to pull those off in a controlled way. It's also possible in some situations that you don't want things to back up. When you think of this as a physical assembly line, that makes a lot of sense. Maybe the bin only has so much space, and if everyone doing step A keeps throwing stuff in the bin, eventually it overflows. And so you need the processes to pause. That's actually where an array blocking queue comes in. If you use an array blocking queue, you can set its capacity. With the linked blocking queue, there isn't a capacity. It can just hold however much. But one thread can come in and add. In the case of the array blocking queue, if there are no more spaces left, it blocks and waits until there is space left, and then it gets to add and go back to what it was doing. And then you can also pull objects out from the queue. And I want a pull here, retrieves and removes the head of the queue, returns null if it's empty, but it waits, it blocks. And so if something that is doing calculation B wants something to do a calculation on and nothing is ready for it, when it calls pull, it will just sit there and block and wait until one of the workers doing calculation A puts something in the queue. So once again, this is the type of thing that because we're dealing with mutable values in here, and because we're exchanging value between threads, this is something that can go very wrong with your race conditions, and if you don't do it right, you can have deadlock. And so the blocking queues they've put all that functionality together so that you can use it easily. The last data structure in here that we'll talk about is the semaphore. Semaphores are a classic parallel data structure, and the analogy that's often used for describing semaphores is you have an amusement park ride, or instead of a ride, think of it as like a house of mirrors, where only a certain number of people are allowed to be in there at any one time. And so every time someone walks in, they get handed a ticket. Maybe there's allowed to be 5 people in there at once. Every time someone walks in, they get handed a ticket. And if someone comes up to go in and there are no more tickets, so then you don't allow them to go in, every time someone walks out, they hand back their ticket. And so you're guaranteed that there's only 5 people in there. The semaphore in your programming would be useful for situations where only a certain number of processes are allowed to access possibly something like a database or some piece of hardware, and you know that if you have situations where if you have more threads on something, it really isn't going to be beneficial, so you limit the number of threads on there. When you create a semaphore, you can tell it how many permits, like the tickets on the amusement park ride, you want to have, and then they have the ability to acquire permits and release permits. So that kind of runs through some of these data structures. We'll come back in the next video and do a simple example of this and look at least one data structure and how we can use it going in between multiple threads.